All right, today we're doing something a little different. We're not just going to learn about a machine learning concept, we're going to solve a crime. So put on your detective hats, because we're about to see how a machine weighs evidence to find the truth, using one of its most powerful tools. But first, let's set the scene. Here's our case. A patient's test comes back positive for a really serious disease. Now, the test is super accurate, so common sense tells you they have it, right? Well, you might be surprised. And by the end of this, you'll know exactly why the obvious answer isn't always the right one.
You heard me right. We're going to treat this whole thing like a detective story. Our job is to figure out what's really going on by looking at all the clues. And this whole idea, it's the very heart of Bayesian reasoning, which is a massive deal in machine learning.
So, to be clear, our case is this tricky medical diagnosis. And our detective's primary tool, it isn't a magnifying glass or a fingerprint kit. It's probability. We're going to use math to cut through all the confusion and find the most logical answer.
Every good investigation has to start somewhere, right? And that's by lining up all the suspects. In the world of machine learning, we just call these hypotheses. A hypothesis is really just a fancy word for a possible explanation. For our case, thankfully, there are only two suspects we need to worry about. And here they are, our two prime suspects. Hypothesis 1, or H1, the patient actually has the disease. And then there's hypothesis 2, H2, the patient is perfectly healthy. It's one or the other. Our entire job is to figure out which of these two suspects is the real culprit, based on the evidence we have. Okay, to really dig into the evidence, we need a special gadget, and that gadget is called Bayes' theorem. Now, don't let the name scare you off. Seriously, don't think of it as some complicated formula. Think of it as our detective's high-tech magnifying glass. It's the tool that lets us update what we believe when new clues pop up. I mean, think about how a real detective works, right? They start with a hunch. They find a piece of evidence, a footprint, a witness statement. And that new clue either makes their suspicions stronger or weaker. The question is, how do they do that in a logical, mathematical way? Well, that's exactly what Bayes' theorem is for. Okay, here it is, the engine behind our whole investigation. I know, it might look a little intense at first glance, but I promise, it's just a structured way of thinking. Let's break down what each little piece actually means, using our detective story. First up, we've got P of H, the prior probability. This is just the detective's initial gut feeling. It's what they suspect before they have any real evidence. In our medical case, this is simply how common or rare the disease is in the general population. It's our starting point. Next is P of D given H, the likelihood. This one asks a really cool what-if question. It says, if our suspect is guilty, meaning if the patient really has cancer, what are the chances we'd see this specific clue, the positive test? It's all about connecting the evidence back to the suspect. And finally, P of H given D, the posterior probability. This is the grand prize. This is what we're trying to figure out. It's the detective's new, updated belief after they've looked at the evidence. It's the final answer. So we have our suspects and we have our magnifying glass. How do we actually run this investigation? We're going to use a technique called the brute force MAP algorithm. And the name really says it all. We're going to be very thorough and check every single suspect. The plan is actually super simple. Step 1. For each of our suspects, H1 and H2, we use our awesome formula to calculate that final posterior probability. Step 2, we just look at the two results, and whichever hypothesis has the higher score wins. That's our most probable culprit. It's called brute force for a reason. We're just checking everything, no shortcuts. Okay, detective, time to open the case file. Here are the hard facts. First, our initial suspicion, the prior, is that the disease is super rare, only a 0.8% chance. The test itself is pretty solid. It catches the disease 98% of the time, but, and this is important, it gives a false positive 3% of the time for healthy people. This is all the evidence we have. Now, before we do any math, this is probably the most important clue in the whole case. Our final answer is going to depend heavily on that starting suspicion. The fact that this disease is extremely rare isn't just a minor detail. It's a massive piece of the puzzle that we absolutely cannot ignore.
All right, let's get to it. First up, we're investigating suspect number 1, the hypothesis that the patient really does have cancer. To do that, we're going to multiply the likelihood of a positive test if they're sick by the prior probability of anyone being sick in the first place.
And here's the math. We take 0.98, the test accuracy, and multiply it by 0.008, how rare the disease is. That gives us a score of 0.0078. Let's just think of this as the evidence score for suspect number 1. But hold on, a good detective never jumps to conclusions. We have to give the other suspect a fair shake. So now we'll run the exact same investigation for our second hypothesis, that the patient is healthy and just had the bad luck of getting a false positive.
Now check this out. The chance of a false positive is 3%, or 0.03. We multiply that by the very, very high chance of not having the disease to begin with, which is 99.2%, and look at that number, 0.0298.
Okay, the interrogation is over. We have an evidence score for both of our suspects. It is time for the big reveal. Let's put the numbers side by side and deliver the final verdict. And there it is, the evidence score for no cancer, which was 0.0298, is way, way bigger than the score for cancer, which was only 0.0078. So our investigation is over. The most probable hypothesis by a long shot is that the patient does not have the disease. That incredibly low starting probability, the prior, was the clue that cracked the whole case.
So, case closed. Our detective did a fantastic job. But this was a pretty simple mystery, you know? It only had 2 suspects. What on earth happens in a real-world problem where you could have thousands or millions or even an infinite number of possible hypotheses to check?
And that gets us to the big catch with our brute force method. It's an amazing approach, it's thorough, it's accurate, and it's guaranteed to find the best answer, if you have all the time in the world. But when that list of suspects gets huge, checking every single one just becomes impossible for a computer to handle.
So while our brute force detective is meticulous and always gets it right, they're just too slow to handle the big city's crime wave. This case showed us just how powerful Bayesian thinking is. But it also shines a giant spotlight on why machine learning needs a whole team of faster, smarter detectives to solve the really complex mysteries out there.